Okay, so the next type of reaction we'll talk about is an acid-base reaction. And an acid-base reaction is just what it sounds like. So it's the combination of an acid and a base, and generally that's going to give us some form of ionic compound, such as a salt. And then we're going to form water. So remember that we said that we have to have a driving force in order to have a reaction. And one of those driving forces that we listed was the formation of a pure liquid. Well, in an acid-base reaction, that's our driving force. So notice that we're forming H2O, and notice it has an L, indicating that it's a pure liquid. So we could also write just the net ionic equation, for instance. So we would just get rid of our spectator ions in that case. So here, what we don't see really playing a part. We don't see that sodium is really playing a part, and we see that chloride is not really playing a part. Because remember, this is going to be a soluble salt, so we could just write it as ions. Okay, so it's not really taking place in the actual reaction. So our net ionic reaction really is just hydroxide, OH minus, plus hydronium ion, or H plus, giving us water. Okay, so the next thing says a common product of many acid-base reactions is water and a salt. So that's what we just said. Okay, acid-base reactions are referred to as neutralization reactions. Why neutralization reactions? Well, because we're neutralizing the acid and we're neutralizing the base. So if we were to have this combination, so we had 1-to-1 ratio of sodium hydroxide and hydrochloric acid, we would essentially end up with a neutral solution. So essentially, all of the base is going to neutralize all of the acid it can. All of the acid is going to neutralize all of the base that it can. Okay, so that's why we call them neutralization reactions. Okay, so it says when the number of moles of acid in solution is equal to the number of moles in base solution, that would give us a neutral solution overall. But it doesn't mean, so here's the important thing, it doesn't mean that the pH of the solution will be 7. And that's because we don't necessarily know where we started from. Okay, so we don't know how much acid was present, we don't know how much base is present. Okay, so don't think that just because we have a neutralization reaction that our pH will end up being 7. That's not necessarily true. Okay, so what do we see here? So in the first solution, so here we have HCl reacting with sodium hydroxide to give us water and sodium chloride. So what's really happening in this reaction? So we have 2 test tubes, one pouring the acid and one pouring the base. And in the beaker, we have just pure water. So in one test tube, we have the HCl. But as we discussed previously, we know that HCl doesn't just exist as HCl in solution. No. So what's going to happen? So this hydrogen from our strong acid will go to water. So essentially we have H2O plus H plus gives us H3O plus. Because remember we said that H plus doesn't really exist by itself. Okay, so it's going to get consumed. Okay, and it's going to get consumed by the water. And then what are we left with? Okay, so we're just left with some chloride ion floating by itself. Okay, so it's not going to react with anything just in this state. In the second test tube, we have sodium hydroxide. Okay, so we have sodium ion and we have hydroxide ion, OH minus. When we put those together, we end up combining OH minus and H3O plus to give us, again, H2O, and then essentially sodium chloride, which would still exist as sodium and chloride ion. So in this one, let me go back. We have H3O plus OH minus, giving us water. And of course, we also have sodium and chloride hanging around. Okay, so that's just a simple strong acid, strong base, acid neutralization reaction. And when we get into weak bases, this starts to get a little more complicated. Not necessarily extremely complicated, but there's a little more to it when you have something that doesn't completely dissociate. So we start getting into equilibrium reactions. This gets a little more complicated. But for just a simple standard strong acid, strong base, they combine, they give you water and some ionic compound. So that's your acid-base reactions. The next kind is gas evolution reactions. Okay, so some reactions form a gas. And this can be due to ion exchange or some other factors. Okay, so here we see that we have K2S, okay, so potassium sulfide, and sulfuric acid, giving us potassium sulfate, and then hydrogen sulfide. Okay, so notice our gas is this H2S. Okay, so there's a few gases that I'll show you that we can form. And remember that when we went over the double displacement reactions, I told you that there are some compounds that essentially just aren't stable. And we have to look out for those. Okay, well, this is an example of that. And I'll get into exactly what I mean in just a moment. So the first one is really just an example of ion exchange. But if we look at the second one, so it says, other reactions form a gas by the decomposition of one of the ion exchange products into a gas and water. So what exactly do we mean by that? So remember, when we did double displacements again, I said that some compounds aren't stable, especially in acidic environments. Okay, so in this reaction we have K2SO3, potassium sulfite, reacting with sulfuric acid to give us potassium sulfate, and then H2SO3. Okay? So the point of this is not going to be a stable compound. Okay, and how do I know that? Well, just sort of from experience. Okay, so what's going to happen? What's going to happen is our sulfurous acid, so H2SO3, is going to break down into water and into sulfite. I'm sorry, not sulfite, but sulfur dioxide. Okay, so I'm going to show you sort of just a list of these types of products that essentially you'll know when I see that that's not stable, and that's going to break down into liquid water and then a gas. Okay, so here's another. So here we have metal carbonates plus an acid will give us CO2, salt, and water. Let's take a look. So we have sodium carbonate, hydrochloric acid. That gives us water, CO2, and sodium chloride. And you can see the net ionic below that. Okay, so notice we have kind of a similar situation. So we have carbonate plus an acid, giving us CO2, some water, and a salt. So what do I say that's similar? Because here I have sulfite, and then I have sulfite here, and sulfurous acid. So similar to CO3, SO3, giving us sulfur dioxide. And here it gives us carbon dioxide. And here we have water. Then here again, we have water. In this, we have also sodium chloride present. Okay, so very, very similar. Now look at the next one. Now we have calcium carbonate plus hydrochloric acid gives us CO2, water, and then a salt. Okay, so very similar thing. CO3 plus an acid gives us CO2, water, and then a salt. Okay, the next type. So that's, again, one type of... So hopefully I've made this clear, but these are all sort of different types of gas evolution reaction. Okay, so the first two were kind of examples of ion exchange. This is a metal carbonate and an acid. Next one is a metal and an acid. Okay, so here we have magnesium being reacted with hydrochloric acid, which gives us H2 gas, hydrogen gas, and then the magnesium chloride. Okay, so this is an example of how you might turn solid magnesium into its chloride salt. Okay, this is also done sometimes to actually purify the sulfur of magnesium. You use a very little bit amount of hydrochloric acid, and that actually makes the magnesium very reactive. Okay, but so the point is here we have a metal plus a strong acid to give us hydrogen gas, and then the metal salt. Okay, so this could also be zinc. I could have sulfuric acid, something like that. Okay, so a metal plus an acid gives us that a gas, so generally hydrogen, and then a salt. Okay, so here we have that sodium bicarbonate, sort of a similar type reaction. So here we have Aqueous sodium bicarbonate is mixed with aqueous hydrochloric acid. Gaseous CO2 bubbles as a result of the reaction. So here we have NaHCO3, that's sodium bicarbonate, hydrochloric acid, which gives us water, sodium chloride, the salt, and then CO2 as our gas. Remember that our driving force in these reactions, so remember before our acid-base reaction, that driving force was formation of a liquid. Remember that in these reactions, formation of a gas. That's our driving force. So remember, we have to have a driving force in order to have a reaction. Okay, so I won't go through every single step of this, but you see in the first, from the graduated cylinder, we have sodium ion and bicarbonate ion. Okay, then in the beaker, we have hydrochloric acid, so we have H3O plus and Cl minus, so just like we did before. And when they combined, they end up giving us CO2, our gas, our driving force, plus the salt, and then plus water, of course. Okay, so here's our list of some of the ion exchange products and some information about whether they'll decompose or not. Okay, so the first one we have, so a metal. So here we have sort of some metal plus SH, so sulfur and hydroxide or hydrogen, then some metal plus sulfide. Okay, so that will react with an acid, and that will give you H2S. So in other words, the product you would predict by displacement. And then it says, will it compose? And so for this one, no, it won't compose. Okay, so what gas is made? Well, we're making H2S. So will it decompose? No, but it already is the gas itself. Okay, so this is one of those things you just kind of have to know. Okay, so I know that H2S is a gas. So if I see that as a formed from a reaction, I know to put a G next to it, and I know that's a possible driving force for the reaction. The next two are the ones I showed you. So CO3, H2CO3, H2SO3. Okay, so these come from metal carbonates, metal bicarbonates, metal sulfites. Okay, it says, will they decompose? Yes, just like we said before. So carbonate gives you CO2, sulfite gives you SO2. Okay, the last one. So I have ammonium and then an anion, so ammonium ion and an anion. This reacts with base. Give us NH4OH. Will it decompose? Yes. What gas is made? Ammonia gas, NH3. Okay, so if you just know these are the only ones I'll expect you to be able to readily know that these are gas-forming reactions. I won't ask you any other ones. There are others, but not, these are the ones I expect you to know. Okay, so there's two more types of reactions we'll talk about. So we're going to talk about oxidation-reduction reactions, and we're going to talk about combustion reactions. So far we talked about precipitation or double displacement, single displacement, acid-base, and gas-evolving reactions. So these are all involved in the exchanging of ions in solution. Okay, so single and double displacement, we were swapping places with ions. Acid-base, we were swapping essentially H plus ions around. And then gas-evolving reactions, we're essentially trading things like CO3 and Na+. So just general ions, what I'm trying to say is just all those reactions involve the exchanging of ions. So other reactions actually involved transferring electrons rather than just transferring entire ions. So you can kind of think of them in the same way as, positive and negative moving around. But this time we're only talking about transfer of electrons. Okay, so when we transfer electrons from one atom to another, we call these reactions oxidation and reduction reactions. In other words, redox for short, so reduction and oxidation. Oh, sorry, I drew my line in the wrong place, didn't I? So red from reduction, ox from oxidation. Okay, so redox reactions. Okay, so many involve the reaction of a substance with oxygen. So oxidation, oxygen. Okay, you can kind of see where they got the name for that, but that doesn't always necessarily happen. Okay, so don't think that, oh, I don't have oxygen, so there's no oxidation. That's not how that works. But generally speaking, oxygen is involved in some reactions. Okay, so here's an example. So we have iron combining with oxygen to give us iron oxide. Okay, so basically a type of rust. Okay, so notice we have to balance it out. We won't get to that in this class, but there is a method for balancing redox reactions. We'll talk about it in Chem 2. But for now, just understand that we're moving electrons around to make these reactions go. So another one of our driving force, remember our last one, exchange of electrons. Okay, so what exactly is oxidation? So we have reduction and we have oxidation. Okay, so oxidation is the process that occurs when, so firstly, the oxidation number of an element increases. In other words, it becomes more positive. So as something like a metal loses electrons, it becomes more positive. So +1, +2, +3. Okay, so if an element loses electrons, that's oxidation. If a compound gains an oxygen, and we'll talk about why that is in a moment. If a compound loses hydrogen, okay, a half reaction has electrons as a product. So what do I mean by that? I just mean I have some metal giving me some metal plus electrons. So E with a little negative sign, that's our symbol for electrons. Okay. And generally speaking, this will occur at the anode of an electrochemical cell. Okay, so the thing people usually remember for that is the red cat. So reduction occurs at the cathode, but in other words, oxidation occurs at the anode. So we'll get to that in a moment. Okay, next thing, an oxidizing agent. You can probably forget about the red cat thing for now. So an oxidizing agent is an electron acceptor. Okay, so notice it's an oxidizing agent, which means it oxidizes something else. It itself gets reduced. So this actually gets reduced. Okay, but it is doing oxidation. That's why we call it an oxidizing agent. So it's an electron acceptor. And it causes another species to be oxidized. But again, it itself is reduced. Okay, the way to remember what exactly is oxidation, what exactly is reduction, there's two ways. And these are, you probably learned these in high school, one or the other. Your teacher probably told you this. So one is oil rig and one is Leo Gur. So oil is oxidation is loss of electron, or oxidation is losing electrons. Rig is reduction is gaining electrons. You can kind of phrase these however you would like, but that's just the general way. And then Leo Gur, lose electrons, oxidation, gain electrons, reduction. Okay, so you can kind of phrase those however you would like, but just generally speaking, that's a way to remember what's what. So oil rig, oxidation is losing electrons, reduction is gaining electrons. And then Leo Gur, losing electrons, oxidation, gain electrons, reduction. So there's a full sentence that's something like, Leo the red cat says Gur, something like that. And the red cat thing, again, comes back when you're talking about electrochemical cells. So that's oxidation. And then reduction is basically the opposite. So it's a process that occurs when the oxidation number of an element decreases, element gains electrons, compound loses an oxygen, compound gains hydrogen, and if a half reaction has electrons as a reactant. So you might see something like this. So you can see M plus E negative gives us M, something like that, where our electrons are a reactant. Similarly to an oxidizing agent, a reducing agent is an electron donor. Okay, so it causes something to be reduced, but again, it itself is being oxidized. So it's electron donor, and it's reducing something else while it becomes oxidized. And again, we have our oil rig and our Leo Gur. So these are really, really handy. You don't have to remember both. Just pick the one you like better, and then go with that. But those are handy because you might be sitting the exam trying to remember what was oxidation, what was reduction. If you just remember those, you'll be good to go. So now that we know what oxidation and reduction are, let's take a look at a reaction. So here we have aluminum reacting with a copper ion to give us aluminum ion and then copper. So in any redox reaction, we should be able to write two reactions. We call these half reactions. So we should be able to write an oxidation half reaction, and we should be able to write a reduction half reaction. And to do this, we first have to figure out what exactly is being oxidized and what exactly is being reduced. And so here it's not too difficult. We have aluminum becoming aluminum ion. We have copper ion becoming copper. Okay, so why do I say this is kind of an easy one? Well, so we're going to learn some rules in just a second, but for now, just kind of go with me. So anything in its solid state like this, so it's elemental state, this is going to have an oxidation number of 0. Okay, so I'm just going to go ahead and write these in. Let's take a look. So we have aluminum going from an oxidation state of 0 to an oxidation state of +3. So what does that sound like? Are we increasing our oxidation number or decreasing it? So of course we know that 3 is bigger than 0. Okay, so we're actually increasing our oxidation number. So that will be our oxidation, essentially our oxidation pair. Okay, so this will be our ox part. And then we have copper going from 2+ to 0. Okay, so it's going down. Okay, so this is going to be our reduction pair. So if we want to write two reactions for this, first if we want to write the oxidation reaction, we have aluminum going to, or giving us, aluminum 3+, and then what? So that wouldn't just be, so if I don't include this next part, this isn't really a balanced reaction anyway. Why? Because I'm essentially destroying matter, right? So I don't have any electrons, so I'm losing electrons, but where am I losing them to? So, okay, so I have to write them in. And I can write electrons just like I write any other reactants or products. So here, so just so that they're just not being destroyed into the ether, I have aluminum giving us aluminum ion 3+ plus 3 electrons. And that's just straight from my reaction upstairs, up above. Okay, so we're losing electrons by a substance. Of course, that's oxidation. Okay, so the oxidation number of aluminum is increasing. Okay, so electrons are donated by the metal. So therefore, we know that aluminum is being oxidized, and we know that aluminum is acting as a reducing agent. Okay, so this are, remember we said these are called half reactions. So this would be a balanced half reaction. Okay, so for our reduction reaction, we have copper 2+ plus 2 electrons, giving us copper metal. Okay, so here electrons are being gained by a substance. The oxidation number is decreasing. Therefore, copper is being reduced, and it's acting as an oxidizing agent. Okay, so just remember, if something is being reduced, something else is being oxidized. Okay, so I can't have one without the other. I can't just write, if I can write an oxidation reaction, I have to be able to write a reduction reaction. I don't have one without the other. And if you do, you've done something wrong, basically. Okay, so oxidation and reduction must occur simultaneously. And we know that oxidation occurs when an atom's oxidation state increases. We've kind of gone over this already. And reduction occurs when an atom's oxidation state decreases. Okay, so and this can be for any molecule or atom. It doesn't have to be just metals. That's very common for metals to be involved with oxidation-reduction reactions, but we also have these with just basic molecules. Okay, so remember, just like we said, something like aluminum has an oxidation state of 0. Anything in its elemental form has an oxidation state of 0. So if we want to go through and assign oxidation states for all these, and again, we'll learn rules for this in just a moment, but here we're going to say carbon is -4, and then we're going to say oxygen is 0, this carbon is +4, and then the hydrogen is +1, here oxygen is -2, then we have water where we have +1 hydrogen and -2 oxygen. So what's the point of this? We want to look for what's being oxidized and what's being reduced. So first we see that carbon is going from -4 to +4. We also see that it's gaining oxygen and it's losing hydrogen. Okay, so that's a good candidate for oxidation. So I'm going to go ahead and assign that as my oxidation pair. Then I have oxygen going from oxidation state of 0 to an oxidation state of -2 and -2. And we'll learn why exactly that is in just a moment. So that's my reduction. I'm going from 0 to -2. Okay, so I'm gaining electrons. My oxidation number is going down. Okay, so that's my reduction pair. Okay, so just remember, if I can identify an oxidation pair, I have to be able to identify a reduction pair. And that's basically what these reactions are all about. It's figuring out what's being oxidized and what's being reduced. Okay, so here's an example of hydrogen combining with oxygen. Okay, so hydrogen and oxygen in the balloon react in the form of gas to form gaseous water. Okay, so here we have a balloon full of hydrogen and oxygen, and we have a candle being placed very close to it. Of course, we know what will happen. The balloon will combust, explode and combust. And so what we're learning here essentially is that combustion is a fancy form of oxidation. So combustion is just the combination of a substance, like hydrogen for instance, with oxygen to give us essentially water, and if we have carbon around, it'll give us CO2. Okay, so this is just sort of maybe a way for you to remember, what exactly is oxidation, what exactly is combustion. Okay, but that's kind of neither here nor there for right now. Just as an example. So here we have hydrogen reacting with oxygen to give us H2O. Okay, so what exactly is happening here? Okay, so we have hydrogen in its elemental state, so that's 0. Oxygen in its elemental state, so that's 0. Here we have +1, and here we have -2. And I'm going to show you how I know these things. Just trust me, we'll get there. But for now, just trust me on these. Hydrogen is going to be +1, oxygen will be -2. So what's my oxidation pair? This would be my oxidation pair. And then this would be my reduction pair. Okay, sorry, it took my pen a second to catch up there. Okay, so essentially combustion is just a fancy form of redox. Okay, so now let's get into our rules. So how do I know exactly what the oxidation state of something is? So if you're familiar with assigning charges, this is going to be very similar. Okay, so free elements in their atomic state have an oxidation state of 0. So an example of this would be a metal like sodium or chlorine gas. These are both going to have an oxidation state of 0. So their atomic state or their elemental state. So in other words, how you would find them in nature. Okay, so remember that we have diatomic gases like oxygen and chlorine in our halogens. That's their atomic state. Those are diatomic molecules, or diatomic elements, you could say. Okay, so anything like that, so aluminum, copper, gold, anything that doesn't have a charge next to it, that's a metal, that's basically the way you'd find it on a periodic table, that's going to have an oxidation state of 0. Okay, then our group 1, our alkali, and our group 1 and our group 2, our alkali and our alkaline earth metals, always have an oxidation state, always. Just going to put some quotes around that. Okay, but generally speaking, always have an oxidation state of +1 and +2. So our group 1s will be +1, our group 2s will be +2. Okay, so fluoride, a fluoride ion, has an oxidation state of -1. So that's pretty much true for all our halogens. You can kind of assume they're -1. Next, hydrogen has an oxidation state hydrogen's oxidation state is mostly +1. So most of the time, if I have something like H2O, something like that, it will be +1. But if I combine it with a metal, it will behave as a hydride ion. In other words, it will be -1 because I have H1-. Okay, so generally speaking, if it's in a molecular compound, it will be +1. If it's more like an ionic compound, it will be -1. And that's not totally true, but if there's a metal around, you can assume it's going to be a -1. Not always, but most of the time. And if there's no metal around, you can assume a +1. Next, oxygen, most of the time, has an oxidation state of -2. Okay, that's our oxide ion. However, it can have -1 for the form of a peroxide, or -1/2 as a superoxide ion. So very rarely will you see hydroxides. So this is like HOOH, that's a hydroxide. Those are pretty rare. So generally speaking, you can assume just as a touchstone that oxygen is -2. Next rule, number 6. The sum of the oxidation states in an atom and of all the atoms in a compound is equal to 0. Okay, so example here, sodium chloride. I have sodium +1, Cl -1. Okay, so if I add +1 and -1, of course I get 0. Okay, next one, the sum of the oxidation states of all of the atoms in a polyatomic ion equals the charge of the ion. Okay, so for instance, I have nitrate. I know nitrate is NO3, 1-. Okay, so if I want to assign the oxidation states within nitrate, the total has to add up to the charge of the polyatomic ion. Okay, so I have 3 oxygen, so I'll call them -2. So that's -6. So then how do I still remain with a -1? Well, I have to make nitrogen +5. Okay, so those are your 7 rules for assigning oxidation states. And you'll notice that they're very similar again to finding the charge of an atom. Okay, so let's see if we can do this one. So it says assign oxidation states, determine the elements that are being oxidized and reduced, and determine the oxidizing agent and the reducing agent for the following reaction. So based on what we just went through, you should be able to handle this one. So pause me, give it a try, and let's see what you come up with. Okay, so let's take a look at this one. So we have 10 + 4 reacting with calcium to give us 10 + 2 and calcium +2. So pretty easy to assign the oxidation states here. The only one we were missing was just calcium on its own, so we know that that's 0. Okay, so we know that 10 is +4 since it's charged +4, and it becomes +2, and then calcium becomes +2. Okay, so we assigned our oxidation states. Now we need to look for what's being oxidized and what's being reduced. Okay, so we see that 10 is going from +4 to +2. Okay, so it's gaining 2 electrons, so we know that's being reduced. Calcium is going from 0 to +2, so its oxidation state is increasing, so we know that it's being oxidized. Okay, so now we've identified what's being oxidized and being reduced. The last thing we want to do is determine the oxidizing agent and the reducing agent. So of course we know an oxidizing agent oxidizes something else. So since calcium is being oxidized, that means 10 has to be our oxidizing agent. And for a reducing agent, we know that, sorry, I lost my train of thought for a second. We know that 10 is being reduced, so that we know that calcium has to be a reducing agent. Okay, so I'll leave that up for just a moment. Okay, the next one, it wants us to just assign oxidation states. Okay, so give this one a try. Okay, so let's go through this one. First one we have Br2. So basically atomic bromine. Okay, so we know anything in its atomic form will be 0, or its elemental form, you could also say. Okay, now we have potassium +1. Okay, we know it's a group 1 element, so it's going to be +1. Next one, we have lithium fluoride. Okay, so again, we know that lithium is in group 1, so we know it's going to be +1. And we said before that fluoride will always be -1. Okay, so we have +1 and we have -1. And since we know they have to be equal to 0, +1 -1 gives us an overall oxidation state or a charge of 0. Okay, next one, CO2. So here, the only thing we really know for sure is that oxygen should be -2. Okay, so we could put in -2 for oxygen. And we have 2 of them, so that's +4. So if we have -2 times 2 gives us 4, -4. So to make this overall equal to 0, we have to add a +4, which would give us 0. So that means carbon must be +4. Let's see if we're right. Get all my writing out of the way. And we are. So -2 and +4. So this is a good thing to kind of note here. If I was to ask you the oxidation state of oxygen in this compound, you wouldn't tell me -4. That would be incorrect. You would tell me -2. So each individual oxygen still has an oxidation state of -2, whereas the total oxidation state of all of the oxygens would be -4. But if I asked you the oxidation state of oxygen, you would still say -2. So don't get tricked by that one, because that's something I could potentially ask you. Okay. Last one, we have our sulfate ion, SO4 2-. Okay, so what do we say about polyatomics? We know that their oxidation states, when they combine, they have to be equal to the charge of the overall ion. So I have sulfur and I have oxygen. So I know oxygen, again, -2, -2 times 4 gives me -8. But I need to have 2 left over. So let's say -2 will give me, and I know this math doesn't exactly work out, so let's get rid of the negative sign. So 8 minus 2 gives me 6. Okay, so essentially I need sulfur to be +6. Okay, and that gives me an overall charge of -2. So if I say 6 plus -8, that gives me -2. Okay, let's check our answer. So of course oxygen -2, sulfur is +6, and it leaves us with an overall charge of -2. Okay, so for some more practice exciting oxidation states, I have some worksheets on the blackboard for you. So do make sure you give those a look. Hopefully, if you go over those, you'll have a better idea of how to assign oxidation states. Okay, so our last type of reaction here is our combustion reactions. And we looked at one of these a little bit earlier. So combustion reactions just means that we're going to combine some molecule. Here we're taking a carbon compound, and we're reacting with oxygen to give us two products, CO2 and water. So what's very important to understand here is in a combustion reaction, I'm always going to have the same two products according to what I'm actually burning. What am I combusting? So if I'm burning something that contains carbon, my two products will always be CO2, and my second product will always be water. Now, how much CO2 and how much water I produce, that's another question. But those will always be my products. Okay, so a combustion reaction is a reaction in which oxygen is a reactant. Okay, so combustion reactions release a lot of energy, we know that. And the combustion reactions are a subclass, essentially, of oxidation-reduction reactions. So we saw that when we looked at hydrogen burning. Okay, so if we look here, we could assign our carbon oxidation state. We know it would be something like minus something, right? I'm not going to actually try to do that math real quick, but minus something. And then we know when we get over here to CO2, it would be plus something. Okay, so we have oxidation reduction occurring. Okay, so remember I said that what we produce depends on what we're burning. Okay, so if we have carbon in our reactants, we'll produce CO2. If we have hydrogen, we'll produce H2O as a gas. So we'll always produce H2O as a liquid, but if we have hydrogen in our compound, we can produce H2O as a gas, water vapor in other words. If we have sulfur, we'll produce SO2 gas. If we have nitrogen, we'll produce NO or NO2 gas. And if we have metal, we'll combine to form a metal oxide. Okay, so just like with the decomposition reactions, just know that if I have carbon, CO2, sulfur, SO2, etc. So what if I want to write the complete combustion reaction for methane? And I want to go over this one with you. So how would I write this? So first I write, my reactant, CH3, OH, and I know it's combustion, so I would write plus O2. I don't know how many yet. And what are my products going to be? So how do I know? Well, it's a reactant containing carbon, so I know. Ooh, sorry, it keeps skipping back on me. Works better when I use my note program than when I just use PowerPoint. So CO2, and of course, water. And put our states in. This is liquid. This will be a gas. This is a gas. And this is most likely probably a liquid, but let's put it in the gaseous form just to keep everything in the same state. So let's say that it's hot enough that it's actually evaporated. Okay, so now what do we need to do? We need to balance it somehow. Okay, so we can write our balancing line, which hopefully I showed this class. So carbon, hydrogen, oxygen. Okay, so here I have just one carbon, I have 4 hydrogen, 3 oxygen. Here I have 1 carbon, 2 hydrogen, and 3 oxygen. Okay, so let's just see how we can make these balanced. So carbon is already balanced, good. Hydrogen, so we have 4 on one side and only 2 on the other. So the only way we can fix that is by putting a 2 here. So that gives us 4 there. Then I have 2 and 2, so that gives me 4. Okay, now my oxygens aren't balanced anymore. Oh no. Okay, so we could keep going through this process, but I happen to know that it's 2, 3, 2, 4. And if we total all these up, so here we have 4 times 2 gives us 8. 4 plus 4 gives us 8. Carbons, I have 2. Carbon, I have 2. So 2 times 3 is 5, plus 1 is 6. Did I do something wrong? Oh, I'm being silly. 2 times 3 is 6, plus 2 is 8, of course. Being silly. Okay, then 3 times 2 is 6, plus 2 is 8. So that's our balanced reaction. So that would be our complete balanced reaction for methanol. So I'll leave that there for a second. And I also have this typed out for you. So if I want to write the complete combustion, so first write our reactants. So methanol and oxygen, here they have methanol as a liquid, that's fine. And then combine oxygen with each element to make a product. Okay, well, but we know already that it's going to be CO2 and water. Okay, so this is just sort of a different way of doing it. Okay, and then basically just balance it. Okay, so those are pretty simple since we already know essentially what the product should be. Okay, so here's 2 more for you. So it says complete and balance the following reactions. So the combustion of acetic acid and the combustion of isopropyl alcohol. So give these a try, write these out, and then I'll go over them with you. Okay, so let's look at the first one. So combustion of acetic acid. So first thing, let's write our products. So write acetic acid plus oxygen. And then look for what elements we have. So we just have carbon, hydrogen, oxygen. So we know our product will be, CO2 and water. Then you just have to balance it. Okay, and that just takes a 2 in front of oxygen, 2 in front of CO2, and 2 in front of water. Okay, so hopefully you got that one. Not too bad. So once you sort of do one of these, they're really pretty much all the same. Next one, isopropyl alcohol. Okay, so again, write our reactants, isopropyl alcohol, and oxygen. Okay, and we know we're just going to produce CO2 and water, since all we have is carbon in the material we're burning. Okay, then you just have to balance it. So put a 5 in front of oxygen, 3 in front of carbon dioxide, and then a 4 in front of oxygen. So notice this number often corresponds to this number. Not always, but it's a good place to start. Okay. So that will finally finish up this chapter. Please let me know if you have any questions.